This is video 48 in the lectures on the design of reinforced concrete beams. This lecture deals with an exercise on pre-stressed concrete. We will design a pre-stressed beam with a span of 15 meters and a rectangular cross-section B times 8 with a total capacity inclusive proper weight of 30 kN per meter in SLS. Estimate the total pre-stressed losses at 20%. The point of gravity of the tendon is situated at 100 millimeters from the bottom fiber of the midspan. Do a stress check in the cross section at midspan. Optimize the pre-stressing force so that there is no tension in the bottom fiber at midspan for load case 2, which is the long-term load case. So here we have to design the pre-stressing force, but also the dimensions of the beam. And the beam must be able to carry 30 kilonewtons per meter in SLS. For a section like that, we have too much variables. We always try to have the width should be half of the depth of the beam. And we will accept a base load pre-stress of 4 megapascal, so that in the section there is a base load of 4 megapascal pre-stressing force. The radius of the tendon profile is L squared over 8E. We don't know yet. The load balancing method Q is NP over R. Needed pre-stressing force P is then Q L squared over 8NE. It is the R is substituted in here. So now we have the needed pre-stressing force as a function of the eccentricity. The base load is 4 megapascal, so it means that with long-term losses, 0.8 P equals 4000 B times H, which is 2000 H squared. And eccentricity at midspan, we know it is H over 2 minus the 10 centimeters. So now we have an equation for the needed pre-stressing force, an equation for the load base, and an equation for the eccentricity at the midspan. So from those three equations, we can say what is the minimum height of the beam. It's 1 meter, and the width is then half a meter. The eccentricity is then H over 2 minus 0.1. It's 0.4 millimeters. The pre-stressing force is then 2,637 kilonewton. The cross section is 500,000 square millimeters. W is then 83 million cubic millimeters. And the bending moment load is then the bending moment on the, with the proper weight of the beam is 351.5 kilonewton meter. And the load from the mobile load, the bending moment for the mobile load is then 843.75 kilonewton meter. So we do now the stress check. The top fiber at midsection, the top fiber, the stress at the top fiber is then with the formula 3.17 megapascal, which is in tension, and the bottom fiber gives us minus 13.71 megapascal, which is compression. This is for load case 1. For load case 2, the top fiber gives us minus 4 megapascal compression, and the bottom fiber gives us minus 422 compression, also compression. This is logic because we have used the load balancing method, and so at midsection it should be like that. And the base load was 4 megapascal. You will see it coming here. But now load case 1 gives tension in the top fiber. It's too high. So solution, less pre-stressing force. So assume now the stress at the bottom fiber is 0 at load case 2. And this is really the limit. So we have to lower down the pre-stressing force because of load case 1. But there's a limit on lowering this pre-stressing force. And this is load case 2, where the bottom fiber, the stress must be bigger than or equal to 0. So we take the load case 2 and the bottom fiber. We put this equation to 0 and calculate P. So we know the pre-stressing force must be bigger than 1861 kilonewton. So we take 1900. And then we do the check again. And you will see the top fiber still has a tension of 1.1 because we optimized the pre-stressing force for the final load case 2, for the bottom fiber, which is in compression, and the top fiber must not be in tension. And in load case 2, we see that we arrived at the 0 or almost 0 compression for the bottom fiber on the load case 2. So that was the aim. So this is complying well. So in load case 1, the tension stress in the top fiber is small and acceptable. This is a temporary situation where the tension is smaller than FCTM, which is around 3 megapascal. To avoid tension in some load cases, it is recommended to partially balance out the load. It means not the total load, otherwise you will have in load case 1 tension. So we can also decide only to balance out the mobile load or 80% of the mobile load. At the design of a beam in prestressed concrete, one has to make choices concerning the specific load that one wants to balance out. You can now optimize the pre-stress in a beam.